In this video, we are going to compute critical times for each vertex. To start, work backwards. The end has a processing time of 0, so that gets a critical time of 0. Moving back to G, it is 8 time units to the end of the graph. Looking back at C, it's 2 plus 8, or 10 units to the end of the graph. Let's work on the top now. F is 4 units to the end of the graph. Coming down to D, we have 3 plus 4, or 7 units to the end of the graph. E to the end is 1 plus 4, or 5 time units for a critical time. Now looking at B, we have a choice. We could either go to E, or we could go to D. Anytime there's a choice, go long. 7 is bigger than 5. 6 plus 7 is 13, so B's critical time is going to be 13. A is going to be 7 plus 5, or 12. And the overall critical time is just the biggest number for the start vertex, so we're going to grab 13 for that. Let's look at every possible path from start to end. For example, we could go start, A, E, F, end. It takes 12 time units to travel this path. Now consider B, E, F, end. It takes 11 time units to travel this path. Now consider B, D, F. It takes 13 time units to travel this path. And finally, consider C, G, end. It takes 10 time units to travel this path. Due to precedence relations, we can never shorten these paths. So when we find the longest one of these paths, we get the critical time, or the optimal time, or the best hope we have for the shortest amount of time to complete the project. The critical time algorithm makes a priority list based off the longest critical time going to the shortest critical time. So for our example, we would start with B with a critical time of 13 but a processing time of 6, then A, C with 10, G with 8, D with 7, E with 5, and finally F with 4. Notice the numbers I wrote in parentheses are the processing times, but the order is based off the critical time. Let's schedule this project on 2 processors. To begin, identify the independent tasks. Looking at the digraph, and we see this is A, B, and C. Circle these tasks on the priority list. Assign task B to processor 1 because it is highest priority, followed by task A to processor 2, also high priority, and draw a line to indicate we are working on these tasks. Task B will finish up first. Go back to the digraph. If B is finished, notice this means D is now available, and we can circle D on the priority list. According to the priority list, C is the next task to be scheduled, so we schedule that to processor 1 and draw a line through that indicating we are working on C. Now processor 2 opens up, A is completed, go back to the digraph. Once A is finished, notice that because A and B are both done, E is now available, and we circle E on the priority list. Once A finishes, we need to schedule a new task. We have to skip G because G cannot be started until C is finished according to the digraph. The next available task is D, so we will schedule D and draw lines to indicate that D is being worked on. Processor 1 finishes task C, so go to the digraph. Notice that when C is finished, G is open up. Circle G on the priority list. G is the next task to be scheduled. Draw a line indicating G is being worked on. In the meantime, D finishes up. Go to the digraph. D finishing doesn't open up F because we need E to be finished before F can be started, and this means that E is going to be the next task to schedule. So schedule E and indicate that we are working on E. E is going to finish up rather quickly. Go back to the digraph. Now that E and D are completed, F is available. Circle F, and it looks like F is the task we need to schedule next. Schedule F, And we notice that we do have a little bit of idle time left over in the schedule, but the completion time will be 16 time units. The total idle time is 1 unit.